This is Shane Picard with another geometry lesson. Today we're talking about the tangent ratio. It's the first ratio we'll discuss in basic right triangle trigonometry. Later on we'll discuss sine and cosine. What are tangent ratios, first of all? Why do they become useful for us? I have here a rather lengthy statement about tangent ratios, but before we read that statement, let's just talk about what a tangent ratio is. Tangent ratio is a comparison of two particular sides in a right triangle. So, for instance, if I have this 45, 45, 90 triangle here, the tangent ratio compares the opposite to the adjacent leg. Well, what do those words mean? First of all, they're relative terms. Opposite and adjacent legs are defined by reference to some particular angle. So let's focus here on angle A for just a moment. This is angle A. And let's suppose that this triangle has lengths 6 and 6. And we'll say that it's triangle ABC. The opposite leg in this particular triangle with respect to angle A is BC. So the tangent of A, tangent ratio related to angle A, is equal to the opposite, which is BC, divided by the adjacent. The adjacent leg is AC. How do we remember that? Well, opposite is across the triangle, and adjacent is nearby. So every time I talk about the tangent ratio of a particular angle, I am simply comparing the length of the opposite leg to the length of the adjacent leg. Notice so far the hypotenuse has nothing to do with this. We're just talking about the legs when we talk about the tangent ratio. So the tangent of angle A is opposite over adjacent. In this case, in this particular triangle, the tangent of A is equal to 6 over 6, which of course you can see is equal to 1. Let's look at another 45, 45, 90 triangle quickly just to see what we can connect up here. Suppose that this is a 45, 45, 90, and I have a leg that is 2. And I ask the question, what is the tangent ratio here? Well, because this must also be a 2, the tangent ratio of angle, we'll call this angle x, the tangent of x is equal to 2 over 2, which is equal to 1. Okay, that brings us to this definition that we have up here. It says, in a right triangle with given angle measures, the ratio of the length of the leg opposite a given angle to the length of the leg adjacent to that same angle is constant, no matter what lengths are chosen for the sides of the triangle. Notice in these two triangles, they're both right triangles, and angle A is congruent to angle X. They're both 45-degree angles. And we find in both of these that the tangent ratio is constant. They both have a tangent ratio of 1. And in fact, we would find that the tangent ratio to any 45-degree angle would always be equal to 1. That allows us to do the following. We have a triangle. It is a right triangle. I'll say that this is 45 degrees. I'll also say that this is 3.5 units, and I'm trying to find this x right here. I write it this way. The tangent of 45 degrees is equal to the opposite, which is x, divided by the adjacent, which is 3.5. Now, because we already looked at this, we know that the tangent of 45 is always equal to 1. So this piece here is equal to 1. That we would normally find in a calculator, but I've chosen to use this special right triangle because we know enough about those that we can actually identify the tangent on our own. So we have a 1. 1 is equal to x over 3.5. We'll multiply both sides by 3.5, and we end up with x equal to 3.5. Now, that is not a surprise to us. We know that because we know how to deal with this particular special right triangle. But the principle here applies to any right triangle, no matter what the measure of the angles are. We'll take a look at one more example just so we can be sure that we know what we're doing. Let's look at a 30, 60, 90. We had a 30, 60, 90 here. And we're interested in looking at this 30-degree angle over here. And let's talk about the tangent of that 30-degree angle. Now, I'll go ahead and assign a value to this side down here as 2 units. And we can suppose then that this is 2 square root of 3, We know that's true because we've already studied these types of triangles in a prior lesson. The tangent ratio is equal to opposite, which is 2, over adjacent, which is 2 square root of 3. And so we find that the tangent of 30 is equal to 2 divided by 2, of course, is 1. So we have 1 over the square root of 3. Okay. Let's look at a second 30, 60, 90 triangle. Suppose we have this one. We're still interested in the tangent of the 30-degree angle up here. And let's suppose that this is 1 unit. We know that this would be 1 square root of 3. And so the tangent of 30 in this triangle is equal to opposite, which is the 1, divided by 1 square root of 3, which is simply equal to 1 over the square root of 3. So in any triangle, any 30, 60, 90 triangle, if we look at the 30-degree angle, we will find that the tangent of the 30-degree angle is always equal to 1 over square root of 3. How does that help us? It allows us to find unknown values in triangles with given angle measures. Again, let's suppose this is 60 degrees, and this is 30. We'll call this triangle ABC. It is a right triangle. Let's suppose we'd like to know the length of side CB. We'll call that x units. And we know that AB is equal to 16. We have AB, we're trying to find CB. What do we do? Well, in a prior lesson, we learned that we could just use special right triangle relationships. But let's see if we can find it with the tangent ratio. We know that the tangent of 30 is equal to opposite, which is x, over 16, which is adjacent. The tangent of 30 is equal to x over 16. Now, because we already worked with this, we know that the tangent of 30 is equal to 1 over the square root of 3. So 1 over the square root of 3 is equal to x over 16. Now we need to solve for x. How do we do that? There's a number of ways we can get there. The easiest way is to take the 16 and multiply both sides by 16. We end up with x is equal to 16 divided by the square root of 3. That is not simplest radical form, but let's just leave it there for a moment just to make sure we know what we're doing. I say that using the tangent ratio, we discern that x is equal to 16 divided by the square root of 3. Let's look at the special right triangle rules and see how we would get there. We know that the long leg of a 30, 60, 90 is equal to the short leg times the square root of 3. So to solve for x here, we divide by the square root of 3. And we end up with x is equal to 16 divided by the square root of 3. Same answer. What does this mean? We find here that we can use tangents in the special right triangles to find the unknown lengths of sides. Now, there are only 2 special right triangles. The rest of the triangles in the world, for instance, a 40, 50, 90 triangle, that's not a special right triangle. But we can still use the tangent ratio to find the missing lengths of legs. The difference is this. When we use the tangent ratio to find the lengths of legs in triangles, we need to have a calculator because we cannot memorize all of the possible values of these tangent ratios. Again, the trigonometric ratio when we compare opposite over adjacent is known as the tangent ratio, and it's used to find unknown lengths of legs. We write it this way sometimes. The tangent of angle A is equal to the length of the leg opposite A divided by the length of the leg adjacent to A. It's a little bit much, so generally we write it in short form this way. The tangent of A is equal to opposite over adjacent. Let's look at an example. We'll use this triangle here, triangle ABC. Suppose that angle A is 26 degrees. And suppose further that we know that segment BC is equal to 12. I'd like to know the length of AC. How do we find it? Well, we set it up this way. We say that the tangent of 26 is equal to opposite 12 divided by our unknown. We'll just call that x. So when we solve this for x, you may recognize that this can be written as a proportion. Tangent 26 divided by 1 is equal to 12 over x. And so to solve this, we simply can switch these extremes. We end up with x is equal to 12 divided by the tangent of 26. Okay, So we'll need a calculator for that. Before we get to the calculator, let me just review some algebra here. In case that seemed a little too confusing or you didn't quite understand what I meant by the extremes, I want to show one more way that we can solve this. Multiply both sides by x. Put parentheses here to keep that all straight. The x cancels. We have x tangent of 26 equals 12. Now we're going to divide both sides by the tangent of 26. Divide by the tangent of 26. And we end up with 12. This cancels. X equals 12 divided by the tangent of 26. We get the same thing either way. Let me just comment a little bit on this expression, tangent 26, before we leave that alone. First of all, this is not t times a times n. It is also not tan times 26. You cannot divide this by 26 to try and solve anything. That won't work. It's not tan times 26. It is tangent of 26. It's the tangent ratio of a 26-degree angle. To us, it seems a little mysterious because we put it in a calculator and we get a number out. That's just because the calculator has been programmed to find that number for us. But please understand that tangent of 26 is a single number all by itself. It is a single quantity, and therefore we can divide tangent of 26 by tangent of 26 and turn it into a 1, which we generally say is a cancellation. Let's go to our calculator and find out what the tangent of 26 is, and then we'll find out what x is. Every calculator works a little bit differently, so you need to figure out how yours works. A couple things I need to say, and that is, first of all, make sure that you are in the degree function and not in radians. You do not want to be in radians. You absolutely must be in degrees for this particular application. So always check that. If you don't know where that particular selection is made, you need to find it in your calculator, because you always have to make sure you're in degrees when you go to run these basic trigonometric functions. The next thing I'll say is simply that because each calculator works differently, you really need to figure your own calculator out. There's two primary ways that the tangent function is entered into a calculator. In some calculators, you put in the number. For instance, I'll put in the number 45, and then you put the tangent function, and so I'll push tangent, and you'll notice we get the number 1. That's the number we would have expected to get. A few moments ago, we looked at the tangent of 45. We saw that it's always equal to 1. So in this particular calculator that I'm using, you put the number in first, and then select function. In other calculators, a lot of the graphing calculators, you put the function in, and it actually brings up the TAN letters on the screen, and then you put in the number. So you need to figure out how your calculator works. Here we have to solve, we're trying to solve down here 12 divided by the tangent of 26. So what I'll do is I'll put in 26, and I'll find the tangent of that number. I'll store that number in memory, and now I'll go ahead and divide 12 by that number. 12 divided by, and I'll do a memory recall, and hit enter. And the number is 24.6. So using the tangent ratio, we were able to find the length of that missing side, knowing only the length of side BC. That's why we use the tangent ratios. Let's look at another example. Suppose we're given this triangle ABC again, and we're told that B is 62 degrees. We're also told that segment BC is 16 units, and we're trying to find AC. How do we solve it? I'll use the tangent ratio to solve for x. I know that the tangent of 62 is equal to opposite, which is x, over adjacent, which is 16. And so then multiplying each side by 16, I end up with x, these cancel, is equal to 16 times the tangent of 62. Now we need to go to our calculator. Run the tangent of 62 first and then multiply by 16. So the tangent of 62 times 16. And we end up with 30 for x. So that is, again, how we use the tangent ratio to find unknown values. What happens if we know the lengths of the opposite and adjacent sides, but we don't know the angle? Let's look at that. In that situation, we use something called the inverse of tangent. In other words, we want to work backwards. before we try this out, we need to be aware of how sometimes this concept is written down. You can see here it says tangent, and there's a little superscripted -1. That is not the same as something like this, 8 to the -1, which you probably remember is 1 over 8. That is not what we're talking about. Rather, this little superscripted -1 simply means inverse. That's all it means. So when we see tan -1, we know that means inverse of tangent. The ways you'll see the inverse of tangent written, you may see atan. It means exactly the same thing. You may see arctan. It means exactly the same thing. Okay? This is the inverse of tangent, inverse of tangent, inverse of tangent. How do we use it? Suppose we have a triangle, like this one, and it's a right triangle, and we know the lengths of the legs are 6 units and 6 units. We'll call this triangle ABC. And suppose we're trying to find the measure of angle A. We want to know what the measure of angle A is. Well, we know that the tangent, and I put that variable in there, the tangent of x is equal to 6 over 6. Well, that's equal to 1. The tangent of x is equal to 1. So we want to be able to ask our calculator, hey, which angle has a tangent ratio that's equal to 1? The way that we express this in writing is to say that x is equal to the inverse tangent of 1. Now, you may remember the tangent of 45 happens to be 1. So we already know that x is equal to 45 degrees. And hopefully you recognize that when you look at this triangle. But how do we get that out of our calculator? What if it's not a 45, 45, 90? Or what if it's not a special right triangle at all? How do we get our calculator to give us that information? Let's take a look. To find the inverses of the functions on your calculator, you'll need to find the INV key. If you push the INV or inverse key, it changes the functions into their inverses. So, whereas you can see here tangent, cosine, sine, if I push inverse, it's now inverse tangent, inverse cosine, inverse sine. You can see there's a bunch of other functions that have turned into the inverse as well. So in our problem, I'm asking the question, which angle has a tangent ratio equal to 1? In order to find the answer, I put the 1 in, and then I take the inverse of that 1. And you'll notice I get a 45. So this tells me that 45 is that angle that has a tangent ratio equal to 1. So I know then x must equal 45 degrees. Let's look at another problem. I have a right triangle. And let's suppose that this here is 8. And let's just suppose that this is 4. I have a leg of 8 and a leg of 4, and I'm trying to find this angle here. I would write it this way. The tangent of x is equal to opposite 8 over adjacent 4. Therefore, x is equal to the inverse tangent of 8 over 4. 8 over 4, of course, is simply 2, so I'll write it that way, 2. And we go to our calculator. We put in the 2, and we run the inverse of tangent, and we have 63.4. So x is approximately 63.4 degrees. Can we also find y? Let's see if we can find y. We know that the tangent of y is equal now to 4 opposite over 8 adjacent. Of course, 4 over 8 is equal to 1/2. And so we know that y is equal to the inverse tangent of 0.5. We go to the calculator, we put in 0.5, and then we run the inverse tangent of 0.5, and we have 26.6. Now, of course, interestingly enough, we can check our work here because we know x now. X is 63.4. We know y is 26.6. We also know that x and y must have a sum of 90 degrees since this is a right triangle. And so we can add 63.4 plus 26.6 just to check to see if we did that right. And sure enough, we get 90. So we did that correctly. So that's how we use tangent and inverse of tangent. We always use the tangent function To find a missing length of a leg, we always use the inverse of tangent to find a missing angle. Make sure you work through some practice problems. As always, if you have any questions, feel free to send me an email.